So I have my matrix A, and if I type my eigenvalues of A, that's what I get. Well, first thing we see different from last time. What's the major difference? Perhaps let me just do what we did before, right? Just to construct one example of what we did before. So my previous A, remember we are divided by these, and let me just make sure they are what we had. Yeah. So this is one of the examples of what we had before, right? If you type eigen of A and versus this time, what's the most significant difference you find? Yes? They are all real, exactly. They are all real. Okay, all the eigenvalues of the second order derivative matrix are real. It's amazing, huh? Well, actually not so amazing. Why? Because whenever you look at a matrix like that, when I look at the matrix, I actually know all the eigenvalues are real. Why do you think so? Because it's a symmetric matrix. You know what is a symmetric matrix? If you transpose it, flip it over, right? Flip over that way, it's the same matrix, right? And just to make the point across, it's also not surprising. Last time when we look at the central difference scheme, right? Remember we have 1/2 delta x on the upper diagonal and minus 1/2 delta x on the lower diagonal. We get all imaginary eigenvalues because it's not a symmetric matrix. It's an anti-symmetric matrix, right? If you transpose the matrix, it'll be exactly the negative of itself. Okay. So if a matrix is anti-symmetric, all the eigenvalues are imaginary. If a matrix is symmetric, all the eigenvalues are real. Right? I'm not going to. If you look at linear algebra textbooks, it's actually a very easy proof you can do yourself. But I'm not going to repeat it here. But you can really easily show that if a matrix is symmetric, all the eigenvalues are real. Okay. So yeah, all the eigenvalues are real, and if I plot it, now it doesn't make that much sense to plot it in a complex plane because they are all real, right? So I'm just going to plot all of them as a function of the number of the eigenvalue count, right? So basically, we see these pairs coming up, right? So there are like two identical eigenvalues, but it's still not very easy to see a pattern. So how about we look at something with a different n? Okay, let's use another n.
Bigger or small?
Up to you. 100. Okay. Let's plot it again. So let's actually hold on. Oh, I think I forgot to compute my. Sorry, I forgot to recompute my delta x. So let's recover what we had before and plot it. So that's the old figure, and I need to, when I set my bigger n, I have to recompute my delta x, and I have recompute my a, and now I hold on, plot it again. Okay, so this is what I had before. This is my new eigenvalues. Looks interesting. What does it look like? Yes? It looks like a sinusoid, right? Yeah, it actually is going to be looking more and more like a sinusoid. And also, on the right side of the sinusoid, what value is it? if I take a grid, right, on the right side of the sinusoid in both cases, what is the value? What do you think is the value here? 0, right? Okay, and it's also not surprising if you analyze it, because because if you look at the matrix, if you look at this matrix, if I plug in a solution U of all ones, what do I get? I get 0, right? I get 0 because if you sum up every row, right, it's all zeros. Makes sense. If I plug in a solution of all zeros, what should be the second order derivative? I mean, if I plug in a solution of a constant, I mean, the second order derivative has to be all zeros, right? Okay, so we have one eigenvalue of 0, and the minimum eigenvalue, of course, is negative. And what does it look like? Looks like negative 40,000 actually, right? My delta x here is 0.01, right? And it looks like my minimum eigenvalue, the most negative eigenvalue, it's something like 4 divided by the square of delta x. So let's try another number to see if it's the same, if holds true. So maybe 10 times larger, okay? And I hope the eigenvalue computation is not going to take too long. Okay. Right, so we now get minus 4 million. All right, still looks like a sinusoid, actually, right? So we have learned two things. One thing is that the eigenvalues are all real and negative, and it ranges from all the way from 0 to something that scales with 1 over delta x squared, right? Which we actually guessed from looking at the numbers in the matrix. Okay, now what does that mean for our choice of time integration schemes? Right, we are going back to our ODE again and again, right? So if I have an ordinary differential equation, which is this case, right? Whenever we discretize a PDE, we get a set of ODEs. And remember, when we solve the equation, here, this always appears on the right-hand side, right? Okay, so first thing we know is that if all the numbers are negative, it doesn't really bode well to the equation if kappa is negative, right? What happens if kappa is negative?
Oh, the eigenvalues are positive.
Yeah, we get a bunch of eigenvalues that are positive. And effectively, no matter what, all the time integration schemes we have studied, really nothing includes a stability region, right, of immediately to the right of the origin on the real axis. So basically nothing is going to be stable, and it shouldn't be, because if you studied, if you're in the math department and studied analytical PDEs, you're going to see that the equation with a positive kappa is not well posed. It's not well posed in the sense that not just it goes to infinity, but like you can coin up solutions. You can coin up initial conditions to make it go to infinity whenever you want. Okay, so if I want the solution to blow up or goes to infinity at 0.1 second, I can make an initial condition that does so. If I want the solution to go to infinity at 0.01 second, I can make another initial condition to make it so. So essentially, I mean, the kind of ordinary differential equations with positive kappa is not physical, right? I mean, it's hard to actually think of any physical systems would have a negative diffusion coefficient. So let's focus on now for the case where kappa is positive. Okay,